Hello, everybody. It is about 4 o'clock on October 23rd, and I am going to go ahead and jump into this lecture. We're going to be talking a little bit today about the ideas related to interactions. And we often care about interactions because interactions tell us about how objects are going to move. And we often term it as interactions are the cause of motion. And when we talk about movement, acceleration, for example, that is the effect. So interactions, those are the causes, but we're going to dive into what interactions are, and more specifically, what are forces. So taking a look in what is a force? That's the first question. Well, what a force is a push or a pull that occurs because of two objects that are interacting with each other. Whenever two things are interacting with each other, there's inevitably going to be some sort of a push or pull associated with it. And that push or pull, well, that is the force. And as soon as two objects stop interacting, well, that force goes away. And really, we categorize these forces into two types of forces. They're forces that are caused by contact interaction and non-contact interaction. So when you're trying to figure out, what is interacting in a system of objects, meaning a bunch of objects together, when you're trying to figure out what is interacting, well, there are only four things that interact without touch: gravitation, the electric interaction, the magnetic interaction, and nuclear interactions. Now, in this class, we don't really care about electric, magnetic, or nuclear. We're not dealing with that this semester. The only one that we have to worry about is the gravitation interaction. And you ask, well, when is the gravitation interaction present? And really, anytime you're on the Earth's surface, anytime you're on a planet's surface, right? Anytime you're on a very, very massive object. So you go to the moon is very massive. You'd have a gravitation interaction. Go to any other planet, you have a gravitation interaction. So that's really the only non-contact interaction that's going to be present. Now, the rest of the interactions are going to be considered contact interactions. And to tell if there is an interaction present of these types, well, there has to be physical touching. Two objects have to be touching for these interactions to give you forces. And we'll talk about each of these in terms, but you probably recognize a few of these words, right? Friction, you've probably heard before. Spring, air resistance, right? These are all types of interactions that occur. And I'm realizing now spring is on this list twice. But we have spring interactions. And then there's other words like normal. You probably know what the word normal means, but it does not mean the same thing as what we think it means literary wise, right? This word normal has a mathematical meaning, and we'll talk about that shortly. But before we get into that, I want to touch base on the idea of forces and specifically how we measure forces. Because you see, forces are measured with a new type of unit. We use the unit of Newton. A Newton is the metric unit for force, meaning this is your base unit for force, and we abbreviate it with a capital N. And how is it defined? Well, the Newton is specifically defined as being the force necessary to give a 1 kilogram mass object an acceleration of 1 meter per second squared. And the first thing we want to take note of is that force, mass, and acceleration, these are three related ideas. And we'll see the three related ideas and how they come together a little bit later in this lecture. But this gives you the base definition of what a unit is, a unit of Newton is. And we can rewrite the kilogram meter per second squared, that combination of units, as a Newton. Newton is what we would call a derived unit because it comes from other units. It comes from the kilogram meter and second squared. And the reason why we take the time to define this new unit is so we don't have to repetitively write kilogram meter per second squared because forces are looked at so often. So we come up with this shorthand of Newton, but the conversion itself is just 1 to 1. 1 Newton is 1 kilogram meter per second squared. So taking a look at force, we have this idea that it's a quantity. There's some numerical value associated with force, right? Related to how much force is necessary to move mass with some acceleration. So there's some number that we can come up with to represent a force, but number is not the only thing that matters here. In fact, when we talk about forces, direction matters quite a lot. And we can imagine the case of having a physics book on a table, right? So we look at this drawing, this black horizontal line, that's a table, and we have a physics book on top of it. And when we take a look at this, we say that there are two forces on it. Now, we'll talk more about the definition of these forces in a second, but there's an upward force and a downward force. Both of these forces have the same numerical value. They both have 20 newtons as their numerical value, but one of them is upwards, one of them is downwards. So they are opposing directions. And when we have forces that are equal in strength, meaning equal number, but opposite in direction, we would call that a balanced force. We would say these are balanced forces. When there exists equal forces in opposite directions, equal number related to the quantity of force in opposite directions, that gives you a balanced force. And, thinking, okay, well, we have this idea of balance, that must mean that there exist unbalanced forces. And in fact, that is true. We could imagine that we take this physics book and we push it to the side. If we push it to the side, then this book will be moving, sliding across the table. And as it slides across the table, it will have friction acting on it. Friction acts on anything that is moving. So we imagine this book, it still has the table pushing upwards and the gravity pulling downwards. We have two balanced forces in the vertical direction, but we have a leftward force of 5 newtons, and there's no force to counteract this. So we would say that this is an unbalanced set of forces. And this unbalanced set of forces, well, it leads to motion. It leads to changes, we would say, in our velocity. This is what Newton's first, second law are about. And as we get further and further into this, we start thinking, well, we have all of these forces acting on an object. Maybe we need some way to describe them, to define these different forces. And to define these different forces, we usually label them depending on the interaction that is present. So first example is what we call the applied force. Now, the applied force is any sort of a push or a pull acting on an object that is done by a person or another object. Honestly, this is kind of just like our catch-all term. If we don't have a good name for a force, we call it an applied force. It just is the name we give to any force that like we don't have a good definition of. And in this example, we have a person pushing a box. Person pushing a box and it's sliding across the room. The force that the person pushes on the box with, we would call that an applied force. And whenever we have an applied force, it's important to remember there must be contact. So we look here between the person and the box. There is contact between the person and the box. So this is a contact force. If the person was not touching the box, the person would not be putting a force on the box. So we keep that in mind, that this is a contact interaction, and that as soon as that contact ceases, meaning the person lets go of the box, when the person lets go of the box, that is when the force ceases to act on the box. The applied force would go to zero. So first force we're learning, applied force. What's another force that we have? Well, common one that we're all familiar with is the gravitational force. So we're all familiar with this because we've heard the word gravity before. Now, the gravitational force, and we often call this weight, right? Weight is a gravitational force. I'll get more into weight and mass in a second, but the weight or the gravitational force, that is the force that a massively large object acts on another object with, pulling it towards. So we would say the Earth pulls on any object near its surface, it pulls it down thanks to gravity. Now, gravity is an interesting force because it's unlike the applied force. It is a non-contact force. If you take a apple, for example, and you let the apple go, the apple will be suspended in the air, but it will be falling downwards. The earth would be pulling the apple downward, even though there's no contact between the apple and the earth itself. So it's a non-contact force. Yes, you can be contacting the earth. That is absolutely true, but that is not requisite for you to have this gravitational force. Now, how do you calculate this gravitational force? You take the mass of an object. The mass is the quantity that describes how much matter exists in an object, and you multiply it by the acceleration due to gravity. And if you guys remember back a couple weeks ago when we were doing the free fall lab, a couple of weeks ago, we found that the acceleration due to gravity was 9.8 meters per second squared, and that is absolutely true on the Earth's surface. But go anywhere else in the universe, and that value will change. If you go to the moon, the acceleration due to gravity on the moon is just 1.63 meters per second squared. This is why if you drop an object in the moon, it falls slowly. It has a less of an acceleration. And ultimately, this is because there's less mass in the moon than there is in the Earth, but not super important here. Just important to understand that the acceleration due to gravity on Earth is 9.8, but elsewhere it's something different. And what does that mean? That means, let's take, for example, you might be about 70 kilograms. This is about the average mass of a person. So let's say you're about 70 kilograms. Well, no matter where you are in the universe, whether you're on the Earth or on the moon, you are going to be 70 kilograms. Your mass does not change. Again, your mass is just how much matter is present. You take every proton, electron, and neutron, add them up, you can figure out what your mass is. It does not depend on anything else other than how many atoms basically are present. But you can calculate the weight by multiplying that mass by the acceleration due to gravity. And you'll see Newton per kilogram here is the unit. Newton per kilogram is the same unit as a meter per second squared. We just rewrite it in that way because it makes it more evident when we calculate out the weight that the kilograms will cancel out, leaving you with just Newton. Anyway, you calculate the weight 70 times 9.8. On Earth, you would weigh 687 newtons. Again, weight is a force, 687 newtons. But you calculate your weight on the moon, 114 newtons. You would feel much lighter on the moon, and you feel lighter because, well, there's less gravitational force pulling you downwards. That lightness that you feel is just how much force is acting on you. So this is gravitational force. And again, always present. As long as you're near a large celestial object, you have this force present. Another contact interaction. Well, now this is the normal force. And the normal force uses this word normal for a very specific reason. I'll talk about it in a second, why we use the word normal. But the normal force is basically a support force. It's the amount of force that an object feels because it is being supported by another object. So take another physics textbook, put it on a table, and the table must be pushing up on the book. And that upward push is what we term as the normal force. It is a way to keep the book in a stable place. Now, why do we use the word normal? Mathematically, when we use the word normal, we are saying perpendicular to the surface. And the normal force is always perpendicular to the surface. We're talking about direction mattering. Direction matters a great deal. Here, the normal force is always going to be upward on a horizontal surface because that's perpendicular. So this word normal, what it really means is perpendicular. The force is 90 degrees to the table, and it just tells us the direction of the force. But again, this force comes about because our object on the table or whatever is supporting it is stable. And it's stable because the table is pushing up, and that support that the table is providing to the book is what we call the normal force. Another force, well, we have the friction force. Friction is something we're probably familiar with. If you ever try to pull a heavy object across the floor, you'll know it faces quite a lot of resistance. That resistance is because there exists friction between the object and the floor. Now, that frictional force can be calculated based on a constant mu. This is the Greek symbol mu, spelled mu. So the constant is a number that just describes like how much stickiness there is between the floor and the object that's sliding across. So something like ice, where there's not a lot of stickiness between an object on ice, it's easy to slide. That would have a low constant mu. Whereas something that's traveling across like like a gravel driveway or something like that, that's going to face a lot of resistance, a high value of mu. So our friction force depends on this coefficient, and it also depends on the normal force, the same normal force we were just talking about. The force of friction depends on that normal force. So you find a value for that normal force, the friction force is equal to a constant times it. And what's interesting is that the friction force will always oppose motion. So we see here in this example, someone is pulling on the crate to the right. Since they are pulling on the crate to the right, the box would be moving to the right. But the friction force opposes that motion. Remember, direction matters. The friction force opposes that motion, so the friction force would be to the left. Okay, another example, air resistance. Now, air resistance comes about because objects falling through or moving through air will experience some resistance because of that air. Now, we are going to ignore it for the most part in this class. It does exist and it will always oppose motion, just like friction. But it's kind of difficult to mathematically figure out. So we're going to ignore air resistance for the most part, unless otherwise said. And if it's otherwise said, you'll be given a brief explanation of what it means. Um, but air resistance, it depends on a number of things. It depends on how fast an object is moving. A faster moving object experiences more of a resistive force. It also depends on cross-sectional area. So a skydiver, for example, before they pull their parachute, the skydiver, while she has a relatively small area that is facing the ground, right? Just the area of the body. And that means we're just going to get a little bit of air resistance. But when you pull the cord and your parachute opens, well, this skydiver, she now creates a greater area because of the parachute giving you greater air resistance. So air resistance depends on a great deal of things, and that's what makes it mathematically difficult to analyze. So we're gonna kind of put that to the side, not worry too much about it. All right, just a couple more forces. A tension force. Tension forces are interactions that occur with strings or cable or wire. And whenever you're pulling on a string, a cable, or a wire, that gives you a tension force. You're putting tension into the rope, and the tension force will pull directly along the string's line on either side. So if we look at this person in orange, the rope would be pulling on the person in orange to the left. But if we look at the person in blue, the rope would be pulling the person in blue to the right. So tension always pulls along the direction of wire, uh, and it's equal on both sides. So if you figure the person on orange is pulling with 20 newtons of force, the person in blue also 20 newtons of force is what they would feel. So it transmits the same force on either side. So when you're considering a tension force, it only deals with cable or rope or wire, and it is only interacting with people as long as that cable, rope, or wire is in contact. Again, this is a contact force, in contact with whatever it is that it is pulling on. So again, contact force. You got to remember this is a contact force. Uh, Moving forward, I think this is the last force we're going to talk about before we get into some other topics. We have one more force that's going to be relevant, the spring force. Now, the spring force is the force that a spring pulls with. Sometimes this is called a tension because you're putting tension in the spring, but we would often more accurately call this a spring force. And if we take a spring and we stretch it, that means you pull this object downwards, then the spring will be pulling upwards. It's trying to restore to its equilibrium place. So if you pull it downwards, the spring will be pulling upwards. And if you compress the spring, meaning you take the spring and you push it upwards, well, the spring is going to be trying to push downwards to negate that change. So you get a force that is always opposite to the displacement away from the natural length, we would call it. So the spring force, well, it's the force that a spring exerts. All right, so we have all this idea, a whole bunch of forces that exist. When we take a look at these forces, we often want to model them. And by model them, I mean let's create a diagram that represents them. And to create a diagram is to create a free body diagram. These free body diagrams helps us depict forces. And here you have an example of a free body diagram. Traditionally, you represent whatever object you're looking at with a circle or a square. And the free body diagram depicts the forces as arrows. You actually saw this in the earlier book on a table example, but the free body diagram exists to show you the different forces that exist on an object. For example, this object would have a gravitational force and a normal force. The normal force indicates to us that this object is resting on a surface. So we keep that in mind. This object is resting on a surface. Why do we know that? Well, the normal forces only exist when there's a contact between the object and a surface that it is on. All right, well, we have a friction force. A friction force exists when an object is sliding across a surface. So again, this object is on a surface. It is also possibly moving on that surface, indicated by the force of friction. And then we have some applied force. Well, this means something is pushing this book, right? The applied force is a contact force that describes a push or a pull on whatever it is we're looking at. So when we have a free body diagram, we can infer a lot of information about what interactions are going on with this object. And in fact, we can take this even a step further and we can start to analyze sort of how the behaviors of these forces interact with each other and what we can expect from the motion. So I wanted to take a look at a couple of examples of free body diagrams, and we're going to start off with the first example being a book that is on a table. Now I'm going to get out a pen and I am going to draw out the free body diagram that exists for this example. So here's my pen. I start a free diagram by representing it as a circle. This circle represents our book. Well, the book is near the Earth's surface. Since the book is near the Earth's surface, there will be a gravitational force going downwards. So I draw an arrow going downwards, and this is the force of gravity. But what else is acting on our book? The book is at rest on a tabletop, so it's not moving. Don't have to worry about friction. But since it is resting on a table, that table is applying a force upwards that is a normal force. I'm going to write F subscript N here for normal force. Now this is, shaky because, again, not great at drawing on a computer, but these are an upward arrow and a downward arrow. The downward arrow represents the gravitational force. The upward arrow represents the normal force. So there's our example of a book at rest on a table. Probably one of the easiest free body diagrams we can think of. We look at the next one. Taking a look at the next one, we have, let me clear. Okay. Let me grab new pen. So here we have an egg falling from a tree on a nest. We are going to neglect air resistance. Again, we neglect air resistance because it's hard to deal with. So what we're going to do is say we have an object represented by this circle. The circle is our egg. And we think about what forces exist. Well, the egg isn't in contact with anything, right? It's falling through the air. Since it's falling through the air, well, it's in contact with air, which would tell you air resistance, but since we are neglecting air, we are going to say no air resistance. So no contact forces. It is near the Earth's surface because it's falling from a tree. Trees are near the Earth's surface. We can make that assumption. So the only force that exists is the downward gravitational force. So I'm going to write F subscript G for the gravitational force, and that is the force of gravity acting on our egg. Okay, what other examples do I have? I have a flying squirrel that is gliding. It's not flapping its wings, it's just gliding from the tree to the ground at a constant velocity. Now, there's an interesting word here, constant velocity. That's going to tell us something. But before we get into that, let's start off with our free body diagram. Our free body diagram is going to have gravity, because again, squirrels exist near the Earth's surface, so gravity is a known force that is acting on our squirrel. What else acts on our squirrel? Well, we are considering air resistance here. We're not going to calculate it. Again, calculating it can be quite difficult. But if we want to know what the air resistance is, air resistance always opposes motion. And since our squirrel is gliding downwards, we would have an air resistance going upwards. I'm going to write F subscript A R for air resistance. So we have an upward force from air resistance and a downward force from gravity. And what's interesting is this word constant velocity, well, it actually tells us something about our forces. If something is moving with constant velocity, meaning it is not accelerating, that means the two forces that are up and down, they're going to balance each other out. Again, we'll talk about this soon. All right. So when you're considering the different forces acting on an object, what we almost always concern ourselves with is not necessarily any individual forces, but something we call the net force. Now, the net force is just a way to combine all of the individual forces that are present. So for example, if you have the case where you might have a tension force and a gravitation force acting on an object, you don't necessarily care about the tension force or the gravitational force individually. You care about their combined effect. And to find the combined effect, well, for vertical forces, we would say it's the sum of upward forces, and we subtract the sum of downward forces from that. So taking a look here at our two forces, we have 1,200 up, 800 down. That means that we have a net force of positive 400. And that positive is important because, again, I keep mentioning direction matters. Direction matters here. And when we say something is positive, that means something is moving up. We've dealt with this in the previous labs on free fall. We say positive is upwards, just like we say right is positive and left is negative, up is positive, down is negative. So if you end up with a net force here that is negative, well, that negative tells you that the net force is downwards. And that is the case in this next one where we have force of air resistance, 600 newtons upward. My apologies. So we have air resistance upward, 600 newtons, and downwards we have 800 newtons. That means when you take the difference between those, the forces up 600 minus the forces down, you'd end up with minus 200 newtons. So that tells you that the net force is downwards, which makes sense. The downward force is larger than the upward force. So when you combine these together, the downward force wins. When we take a look at this third object, we see the upward force and the downward force are identical, meaning that the net force for our vertical forces is 0. But that's not the only forces that act on it, right? We have this third friction force. When we deal with our horizontal forces, we say that it's going to be the sum of the rightward forces subtracting the sum of the leftward forces. And here we have 0 rightward force and 20 newtons to the left. So we combine those and we would get negative 20 newtons, or we would say that the net force is 20 newtons to the left. And here we have the result of each of our calculations just rewritten out so that we can be absolutely clear. Now, when we take a look at our net force, we can find that our net force is sometimes equal to 0. And when our net force is equal to 0, we call that balanced forces. And whenever forces are balanced, that is a determination that says our acceleration is equal to 0. This is Newton's first law. Newton's first law says if your forces are balanced, your acceleration is 0, meaning that your velocity doesn't change. You stay with the same speed in the same direction, or you are staying at rest. Both of these are cases of balanced forces. You can have 0 net force but be moving, but what it means is that you are not changing your velocity. So these are the sort of two outcomes that can occur from your balanced forces. Either you are at rest or you are going to be continuing to move with the same speed in the same direction. But what if your forces are not balanced? If you have a net force, then that is the case of what we call Newton's second law. And Newton's second law tells us really two things. The first thing is that if you have a crate that you are applying a force to, for example, if you have a little force, meaning you're not pushing very hard, you would have a small acceleration. But if you have a much larger force, indicated by a much harder pull, then you have a larger acceleration. So your acceleration increases if your force increases. A large force means a large acceleration. That's half of Newton's second law. A large force means a large acceleration. But that's only half, because we can also see that if you're pushing something that has less mass and you're pushing it with a lot of force, you get a lot of acceleration. This is what we just saw. But if you push something much heavier, a larger mass, with the same force, the same amount of strength, you would get a smaller acceleration. So what this tells us is that a large mass means a small acceleration. And in any of these cases, we see we have some acceleration, but the strength of that acceleration might change depending on what it is we're applying the force to and how much force we are applying to it. And we would say that for any unbalanced force, there exists acceleration. And this acceleration exists that will be directly net force, meaning more net force, more acceleration. And it is inversely dependent on the mass, meaning more mass means less acceleration. And we often put this into equation form as the force acting on an object is mass times acceleration. We can rewrite this a couple of ways, right? Often we care about the acceleration, and the acceleration would be the force divided by the mass of an object. And if for whatever reason we knew what the mass acting on an object was, if somehow we knew what the mass acting on an object was and we didn't know, or sorry, my bad. If for some reason we knew what the acceleration is and we knew what the force acting on an object is, we can find the mass, and we find the mass by taking the force and dividing by acceleration. And that would give you the mass. And this idea of Newton's second law, well, this is actually what most of this week's lab is focused on. I'm going to go ahead and stop sharing for a second. I'm going to pull up the pivot lab that we're working on, the pivot activity, I should say. So let's go ahead, share screen. Let's share screen two. Yes. So our lab this week, we will analyze the motion of a turbine pushing some masses, and we are given the mass of the object. So in my video here, it's 1,600 grams. We'll probably need to convert that to kilograms. And we have a fan that is going to be pushing on the object, and we can see the fan is pushing with 1.5 newtons of force. And we can see its velocity increasing over time. Now, it does give you velocity here. And past weeks, we've been calculating velocity. So there is an assumption, like you would be able to calculate this velocity if I asked you to, but I'm not asking you to take those steps because what we really care about is how does this force affect our velocity. So the focus here now is more on the force side and the relationship between force and velocity. So there's an assumption that you can calculate velocity, but you're given it here. Now, one thing I will point out, let's go way back to the start. Let's zoom in, take our video. If you look at the video on the far left, we have a spring. And our spring is stretched out as our fan pushes forward, right? That means we have a spring force because we have that contact force. We have a fan giving us an applied force. We have gravity pulling downwards, and we're on a track being supported, so we have a normal force. So that'll help us as we look at our free body diagram and determine what is our free body diagram going to be. where the purple force here in these instances is the applied force from the glider pushing or from the turbine pushing forward. We have normal force of the glider, gravitational, spring force being represented by the green. When you look at asks you for two instances of time, first, while the spring is connected, and then the next one is after the spring is disconnected, we cut the rope. And again, we need to consider what forces are here, and that is a question of what is in contact with our cart. Going further down, it's going to ask us to for our fan, choose different trials here, and the different trials are going to be related to different forces. And for each of these trials, we're going to figure out what is our force, what is our change in velocity, what is our time, and then figure out the acceleration. Now, I want to show you something here, and this is important. This can help you. You can do the calculation, right? We know acceleration is just change in velocity over change in time. So we can say here, maybe our change in velocity is 100 centimeters per second, and it does that in 2 seconds. Then I would know that that's 50 centimeters per second squared. We take our change in velocity, we divide by time, that gives us our acceleration. However, we can make life a little easier on ourselves. And you say, how do you make life easier on yourself? Well, you're going to make life easier on yourself because what you can do is come over here, click on the 3 dots on your acceleration, and you can use a tool here to add a formula to your acceleration column. Or what I'm going to do is click that, and then it gives you a little bar here that you can enter a formula. For example, I could use 987. If I submit that, the formula is 987. It just puts that in everywhere. But that's not the formula. I'm going to change my formula. I'm going to delete that. And what I want to do for our acceleration is take our change in velocity, and I want to divide that by our change in time. And when we do that, it'll automatically calculate our acceleration. So let's say for the next trial, maybe I had 75 centimeters per second as my change in velocity in 2.8 seconds. Well, if I put those into the formula, it will automatically give me my acceleration calculated out for. Now, do you have to do this? No, you do not have to do this, but it is a way for you to more quickly do your work and have the computer do the calculations for you. And this is ultimately one of the things we love to use computers and spreadsheets for in science. And then coming down here, we want to plot acceleration versus force, and that would tell you something about your object. You will interpret that graph and tell us what does your graph mean. There's a reflection assignment. Again, this is just another Canvas discussion post that you need to make for this week. This one is going to be focused on posting a picture of your graph. And then what you're going to do is you're going to use the picture of you're going to look at another person's graph. And from the other person's graph, you're going to determine what the mass of their cart was. You're going to learn how to determine the mass from a graph a little bit earlier on. Okay. So that pretty much wraps it up for the sort of experiment for this week and all the information you need to know. If you have any questions, of course, you're always welcome to ask. Otherwise, I will see you next week. Goodbye.